Okay, so we'll get started now. Today we have our own Brandon Shapiro who will tell us about adaptives, which is a new concept that the Poly group has been working on. So.
Thank you. And thank you for having me. Is the mic working all right?
I think so.
Great. Okay, so I'm going to talk about adaptives today, which has been sort of the subject of some of our work here for the last few weeks. And I'm going to start by talking about something we've gone back and forth referring to as, among other things, the eating problem. But you'll see it's not just about eating. So what is eating? So maybe we have a big box which has two things in it, and a smaller box where we don't worry about what's in it. And these boxes both interact with the world around them. And we could think of this big box as like a person, sort of a complex entity, and maybe this smaller box is like a cookie that they want to eat, which would then bring it into this medium box. But another way we can think of this is that this box is Topos. This box is me. So I've been eaten by Topos. So we're going to model that. And then Topos has some people inside it. I'm not going to write everybody's names, but I've picked the shortest ones. So we'll say Topos contains Tish and Evan before I get here. And then what does Topos do when it's decided to eat me? Well, we still have Tish and Evan. Hi, Tish. You're a part of the talk.
Oh, good.
You and Evan are inside Topos and about to eat me.
Of course. Well, we are voracious, aren't we, Evan?
So we still have Topos, Tish, and Evan, and we still have me out here. But now Topos has, so previously Topos sort of took the input, it went through Tish, then it went to Evan, and then it went out into the world. Interpret that however you will. But Topos could change its state, where now Tish is sending output from Topos, and Evan is accepting some from the world. The big box is the world. And then here I am over here, still doing my thing. But then the world, sort of as part of the same process that had Topos evolve to open up like this, the world changes its state so that I get wired in to Topos. Like this. And then now we have a sequence, sort of like before, but with three of us. I am now part of the sequence. And the Topos box doesn't really make sense anymore in the way it was, because it wasn't really a Topos box. It was a Tish and Evan box. And now a more appropriate Topos box, even though it's really not the same box, would include all three of us. So we sort of went from there to there, and these two you can really think of as the same. Yeah.
Topos on Tuesday.
Exactly.
At 8 a.m.
February 1st. That's when I started here. So, well, maybe not at 8 a.m. So the point of adaptives, among other things, is to be able to describe processes like this, where we have some organizations which evolve based on their state. Topos, the state of Topos made it such that it decided to open up to hire someone. The state of me was such that that made sense to go along with. And the state of the world made it possible for us to link up together. I'm very happy with that. But how do we describe it with math? So the key principles here are organization, which is sort of how these things link up to each other in the world or in Topos, and also dynamics, which is how how the organization changes. And so I'm going to talk about both of those.
So can I just ask you one question?
Yeah.
So this is a snapshot at one point in time, but at any given time in Topos it can change, and often it does, day to day, hour to hour.
Yeah.
Are you going to take that into account in your dynamics?
So when Toby was here, we talked a little bit about dynamics that can kind of evolve continuously in time. Here, there is a presumption of discreteness,
Okay.
I think.
All right.
It's something we're definitely interested in, but we haven't really. I don't think our formalism handles that just yet.
Okay.
But people have thought about it. And it's a very good question. So, and I guess, some interpretations of fundamental physics say that maybe it is discrete in some sense. I don't know. There are people in here who probably know more physics than me and
Might
might
change
contest
the
that.
reason.
For example.
Yeah, maybe.
What?
It could change once a minute, for example, or once
Yeah,
a
yeah,
second.
and it
Yeah,
often
that
does.
he'll take into account.
Yeah, okay.
Mm-hmm. Yeah, so if you pick a finite length of time, then you could hypothetically model it using this formalism. All right, so I'm going to start by telling you a little about how we model organization and then dynamics, and then I'm going to put them together. So let's start with organization. So we're going to start with a set of contributions, which I'm going to write as C. And I'll give an example in a second. So our example could be that C is the natural numbers. Maybe that's hours of work, we could say. That's one type of contribution. But in addition to that, we also want to have, for every contribution, or every possible contribution, a set of possible returns. So returns could be, say, non-negative real numbers of money. So the contributions are the hours you work, and the potential returns are some amount of money. And we're not going to correlate those, but we are going to use them to talk about how people can be organized. And so I'm going to go in and out of different levels of formalism here, but one thing I'll mention is that we can think of this data as a polynomial, which looks like this. So it's indexed by some set, and it has exponents, which are also sets. And then it's also worth mentioning that in this case, this is just going to look like n times y to the non-negative reals. And these monomials are really helpful. And just to connect it up with these diagrams, in this case, you can think of this as a box. it takes in a real number and outputs a natural number. But I'm not going to use that just yet. Okay, so here's where we're starting. Where do we go with it? So, yeah.
It's more sensible to have the opposite, right? For each number of hours worked, you would have a resource that's a number of dollars.
Yeah, so that's a really good point. And like, it would make sense, because then it would be sort of causation, right? Like you work some number of hours, you get some amount of money. Here, it's not so much about modeling what happens, but rather how the contributions are organized. And so in pictures like this, you could say maybe money comes in to Topos, and Tish is involved in managing that money. That money then goes to Evan, and Evan writes a paper, which gets output. And then in this new model, maybe that money goes to me. I come up with some math, and Evan writes a program to implement it, for instance. So maybe that gives some sense of why this might make sense.
But mathematically, why do you want it like that then?
Different examples feel better or worse with that ordering, I admit.
Right.
Yeah, I think that's the best answer I can give for that. This example is meant to be simple, but once we, yeah, I'll leave it
You
there.
output work and you take in money.
That's one way to put it.
Symmetric, so you put, there's a DACA picture, or like you can opposite the category.
Yeah.
And then just put
It's all.
the same function.
I think it's also key that time is really not a factor here. This is more about like your interface with the world, and so this is more like what comes in, and this is more like what comes out, even if sometimes the timing is reversed. Okay, so what actually happens here? So we want for each potential number of people, we're going to have a set called Sn, and I'm going to call its elements n-ary arrangements. And so what do I mean by an n-ary arrangement? I'll get straight to how we use them, which is that for all arrangements in Sn, we have a way of combining n different contributions into one, or arranging n different contributions into one. So I'll go back to the example. So we could say that Sn is n tuples of natural numbers, which we could think of as like efficiencies of n different tasks that people might be doing. And then when we have, so we have n of those, I'll write those as E1 through En, and this gives us a function from n contributions to a single contribution, which will just be E1C1 plus up to ENCN. So maybe we're assigning the first person to a task that generates a lot more work output. Second person goes to a task which we also need, but is slower for some reason. And so that's what I'm going to call an arrangement for now. And then in addition to the arrangements, we also need a way of distributing the returns backwards. So here we have R. Okay, so I'm going to have to give this a name. I'm going to call this AC. So we have the returns on AC of C1 up to Cn, and we have to now go backwards to get a return on our C1 and all of them up through our Cn. And so in this example, what we could do is, given a return, so here all of these are just real numbers, then we could send that to the tuple where for each I, it looks like EICIR over E1C1 plus ENCN. So what this is doing is it's taking some return from this arrangement of work, and it's saying, okay, well, based on how much each of you contributed, including your efficiencies, you get that proportion of the return. Now, you might want to say, well, you know, you didn't have a choice in how efficient your task was. We should only scale it based on the amount of time you spent, which would be reasonable. But one of the things that this formalism does is it imposes some conditions. And that ends up affecting the kinds of arrangements that we can make. So what that looks like is that these sets Sn are going to form an operad. So this basically means that we can treat them as a coherent grouping of n-area arrangements. So for instance, you always have an identity arrangement where you just have one person and they do the normal thing, which we haven't really defined here, but we could. And then you also have a way of, if you have an n-area arrangement, you can also arrange the outputs of other arrangements. And when you do that, you get an arrangement that handles a much larger number of people, generally. So how would we do that in this example? So we could say this is just the number 1. So if you have one person, you can assign them a task with efficiency 1. And in here, this is going to be a big mess to write, but E1 through En, E11 through E1, M1, and so on. This could go to, you just multiply each of these over. So this would be like E1, E11, E1, E12, eventually En, E1n, and so on. And the point of this is,
that should be En1.
oh, thank you. And eventually you'd get to like En, E, N, Mn. Yeah, okay. Oh, sorry. A little better. Cool. This won't be, oh, you all right? The details of this won't be super important, but it gives you a sense of how you can distribute arrangements of arrangements and get a larger arrangement. And in this picture, we want to think of that as removing intermediary boxes. Like here we want to think of this outer world as something in S2, because we have me and we have Topos. What's inside Topos is also S2, because we have those two things. There's not, I guess I could be S0, because we're not looking at anything inside me. And then when we forget the box, we get, oh yeah, yeah, we want to keep me. And then here we get S3. And so that comes from S2 on the outside, cross S2, S1. And when we forget this box, we go to S3. So that's kind of the idea.
But so the if we use this operation on like in this picture, there's also the dynamism that you haven't talked about yet. Like
Yeah.
The composition of these boxes is this box, but where you erase the Topos box, it's not that box.
Oh, definitely, yeah. So like these lines are being strictly enforced, I would say. So there's dynamics from here to here.
Right.
But I wrote an equal sign here because here nothing's actually changing.
Okay.
We're just unboxing.
Right. I guess what I'm saying is yeah, I think I think I understand what you're saying. If you're drawn the S2s in the middle picture, then the correspondence between the S2s and the S3 would be just this operation.
Exactly. And if we want to make that precise, we can put a little box in me to make this even. And then we have some element of S2, S1, and S2. And it's an element of this. Like this particular wiring is some A in S2. This is some B in S2. This is some, maybe this is 1 in S1.
So this articulation says nothing about the relative risk and vulnerability of each of these activities or functions, correct? It's just a description.
This is a description of the possible arrangements in our organization, which I'm casually calling it because we haven't really fixed a name for this particular thing yet. And the only things we consider are what happens when you take arrangements of arrangements. So we want these to form an operad, namely we have this structure plus some equations that I'm not going to write down. And we also want our polynomial, so I'm going to call this P for future reference. P is an S algebra in poly.
To just follow up on Tisha's question, can you not consider those sort of concepts like risk and vulnerability types of contribution and return? Or is it not so?
You could. So you can factor lots of different things into contributions and returns, but one thing that is notably missing here is the correlation. We don't have a way of saying that this contribution gives you this return. That part is left hypothetical. And so it might be of interest to say that certain contributions carry maybe a probability distribution of certain returns. This structure doesn't yet account for that.
But you have some sort of relation that just is, but yeah, you have a possibility.
Yeah, so each contribution has a certain set of possible returns, and you could restrict those based on the type of contribution. Yeah, that's a good point. And we've thought about some examples where that is the case, where you're bounded in some sense. Yeah, thanks. That's a good question. So I'm not going to write down all the equations for what this means, but the point of it is that when we do these compositions of arrangements, that imposes more equations on these functions. So for instance, if we did, so I'll just write down one of them, which is that if we had, let's say, A in here, A1, AN in here, we can go from CN to C, and then we can go from C of that sum to Cn by applying A1, C, and C. I think that type checks. And then we want this to equal don't have notation for this yet. I'm going to call it circle. We want that to equal A composed with A1 up through AN on C.
It says that if you organize Topos or something into multiple levels, then the contributions as being nest.
Yeah.
Maybe you could say.
Yeah, so that's a good point. So the way to think about this, like I said, it's all about unboxing. This is saying that when you remove the boxes, the output is unaffected. So if, in this example, Evan produces an output, which is then sent, and then which is the output of Topos, and then Topos produces an output to the world, and we forget the box, then here it's that same output that Evan is sending to the world. Yeah. And then the analogous equation for the returns basically says the same thing about the inputs. Yeah.
Okay, well, I have two questions. So the first is a check for understanding. So like, before you wrote the last bullet point, I was like, oh, this feels like a sub-operatic poly with one type. Is that?
Yeah, so one way of defining this structure is as a map of operads from S to poly. If you think of S as a one-object operad.
Because every A and SN gets what you just said.
Okay, cool.
Yeah. So yeah, that's exactly right. Did you have another question?
My other question was, over there, P is the poly, and over here is the algebra. Is there something obvious?
Yeah, sorry. So when I say an S algebra, I'm treating S as a one-object. Yeah, a if S is a one-object operad, then yeah. Okay. Cool. Any more questions? I've moved in and out of different formalisms and different pictures here, so if you have any translations, yeah.
Yeah, so over there, the operad looks like an operad of wiring diagrams.
Mm-hmm.
Do you do examples with that operad as well, or just, as opposed to this SN here, which is this?
Yeah, so this S is kind of boring, mostly because it was faster to write down than any of our interesting examples. We would like to do something like an operad of wiring diagrams. We're more interested in working with that when we put the dynamics in as well. And that's kind of the hard part right now, deciding what kind of information the states, which are what I sometimes call the elements of these SNs, what information we want the states to carry in determining how we do these wirings. But this is something we're actively working on. In particular, trying to get one that can like have the world talk to Topos and potentially to me to communicate that Topos needs to open up like this, while the world also knows that once it does, to then rearrange us like that. So yeah, getting the operad to communicate sort of in and out of itself that way is what David has called the eating problem, and we think we might be able to solve it. So this has all been about organization, how different boxes are organized with wires, or how different groups of people are organized in the tasks they do for an organization. But we also want to incorporate dynamics into this. So what I'm going to do, I want to keep these pictures, but I'll use the bottom of this board. So again, we're going to consider a polynomial p. And I'm going to write p a little more generally now. 1y. Like before, p of 1 is a set, p of I is a set for each element of it. And then what we want, the way we talk about dynamics is that a p coalgebra is a function, just a function of sets, from some S to the set P composed with S, which is we just plug in S for y. Y is our variable. And this encodes dynamics, but I'm going to say a little more about how. So in particular, a function from here to here corresponds to, you have a map from S into P of 1. I'm going to call that F1. And then for all states in S, we have a function from P bracket I into S.
Is I F1 and S?
Oh, yes, thank you. So what this is saying is that for every state, we get one of these positions in our polynomial, which in this case we can think of as a contribution, in this case as a contribution. And for every direction, every return, we get a new state.
Now I'm getting confused because you see, the essence started life over there, right?
Mm-hmm.
And then they became an S.
That was an intentional choice. I promise it will become relevant. Those SNs are going to be the states of a dynamical system in a minute.
Okay, I'll wait.
I can't.
Okay.
Okay.
She'll let you know.
Yeah, no, good. Thank you. Yeah, so this is perhaps a temporarily suspend your disbelief at my notation, but it will become relevant soon. So I'll do a quick example for the dynamics. So let's say that S is non-negative reals, P of 1 is also non-negative reals, and every P of, what did I want to call it? Well, every P of I is also non-negative reals. So when we do this then, we get, so I want you to think of S as your bank account balance. P of 1 is going to be the, so that's your account balance. P of 1 is expenses, and the returns are going to be income. And so I can write one of these dynamical systems where our F1 from S to P of 1 sends our account balance, little s, to S over 2. So that means that every month you spend half of your account balance. And then Fs which goes back to S. So then whatever your account balance, whatever your income is, that gets added to the half of your account that you have left.
It's a dynamic in the sense it can just keep happening.
Yeah. And so you can keep doing this. You start with S in your bank account, you spend half of it, you get R, now you have S over 2 plus R. You spend half of it, you get some new return, and the process continues.
And the new return is different from the original R? Or?
Potentially, yeah. So you sort of take in a stream of R's, and then this sort of tells you how your account balance evolves over time.
So you actually have like an R1 and R2 and R.
Yeah, exactly.
Which may or may, the R that came in may or may not be a return on the action.
Yes, in this case, those are taken as variables. So if you get incomes R1, R2, and so on, then all this tracks is that your balance becomes, so if we start with an S and S0, then we get S0 over 2 plus R1. So I guess we start with S0. S0 over 2 plus R1. S0 over 2 plus R1 over 2 plus R2, and so on. And so that's sort of how the dynamics works here.
And is that a continuous fraction?
Yeah. So now we want to combine these two things. We've got ways of organizing people or things in an organization, and we've got ways of a state changing over time and determining some activity, in this case expenditures. Because it's not just your balance, it's also how much you spend. That's a different part of this theory. And so we want to combine the two. And I'm going to tell you how to do that. So. So, no, I shouldn't have erased that. So if we keep this idea of P having a set of contributions and possible returns on each contribution, what we want is a coalgebra on a certain polynomial called p to the n bracket p. Haven't told you what that is yet, but I'm going to. So this is the sum over maps of polynomials from p tensor n to p of y to the for all C1 through Cn p, so I'm going to give this a name.
It's called R stuff, that thing, right?
Oh, yes, thank you.
No way.
Yes. Okay, so why this polynomial? What does that have to do with anything? So here's what we get. So if we have a coalgebra for this, then it's going to be a set Sn, carefully chosen, goes to the sum over p. I'm not going to write this down again. So we get a map from Sn to this with Sn plugged into here. And I can break down what that means in particular because this map of polynomials encodes a lot of information. Namely, for each, so for all arrangement in Sn, we get a map which I'll call, so if this is f, I'm going to say f of c at a. So this goes from c to the n to c. This is like what we had before. And this is just the part of this map on C. We also get, for all C1 through Cn in C, maps, which I'll call FR of A. And so this goes from the return on FCA at C1 through Cn. It goes backwards to RC1, RCn. So this is just in this map of polynomials P that we get for each A. Going from Sn to this applied to S. First you have to pick out one of these. All of this is encoded there. And this is what I wrote down before when describing organizations. But now we have one extra piece, which is for every return in here, we get an element of Sn. And so we also have from this set of returns for the arranged contributions of C1 through Cn, we get a new element of Sn. And this is saying that we start with some arrangement, we use it to determine how to combine our contributions, and that also tells us how to distribute the returns. And then based on what return we get, still not knowing how we get that from the contributions. That is still left variable. But based on whatever return we get, we pick a new arrangement. And this takes us a step closer to something like this, where what's on the wires, namely the return and the output. The output is C, is our element of C, and the return is the input, what comes in. And based on that information, we change our state. The state is where the state is sort of the data held inside the box.
You mean the arrangement?
Yeah. Sorry. The state of the system is, in this case, an arrangement. Trying to keep the words right. Also, all feedback on terminology I use is very appreciated. It's not at all fixed, and I've probably mixed some of it up several times already. So this is what we're using to just, sorry, was there a?
Yeah. You go first.
No, I don't have anything. I was just kind of agreeing that carry on here, but fair enough.
Yeah. So in this new arrangement, the returns in an organization don't necessarily go to the named parties or even that system. They might go to a totally new and different.
Yes, the new state can completely change that. Now, in practice, when we're actually defining this, so when we're saying, you know, given this state A and given these inputs and given this return, what new state do we get? Most often, and in fact in the example I'm going to talk about, it is done sort of incrementally. It's usually like changing it a little bit, not too much, unless you're in a system that is designed to radically change based on.
Or a startup.
Yeah. Like, some systems are meant to be more stable than others.
Yeah.
Something we have talked about is sort of measuring that, like how stable they are or how much things approach what the contributions seem to think they will. These are still kind of vague notions.
Okay.
But yes, that is something we're thinking about, and in a lot of examples that just happens naturally.
Great.
And I think I'll have time to very briefly talk about one of those. But before that, are there any more questions? Okay, so the one last thing I'll mention before I do an example is that, again, we want the SNs to form an operad, P to be an S algebra. This is just like before, and we want the updates, which is what I call this change of state, and we want the updates to respect the unboxing that the operad encodes. So what that means is it should be the case that if the Topos box changes from here to here, and the me box changes from whatever I didn't draw in there to this, and the outside changes from this state of affairs to this one, then if we had erased this box in the first place and seen what would happen in S3 over here, it's the same thing as if you remove the box after doing all the updates inside and out. And this is a pretty stringent condition a lot of the time. Like, and that's part of what's making it hard to write down like a good formal description of this kind of rewiring process. Because what's outside in S2 needs to encode both doing these kinds of rewirings and deciding sort of in this copy of S2 when to go from here to here. And so it has to kind of do a lot of things at once. But we hope that if we can figure that out, then it will tell us a lot about sort of these nice multi-layered systems. All right. If there aren't more questions, I want to tell you about an example. So really quickly before I do, we will also sometimes consider coalgebras which output more than one thing. And so the way I think of that in this picture is you have sort of multiple small boxes. So maybe you have like 3 small boxes, and then these, say, 2 outer boxes, and you kind of have different ways of wiring. You have different ways of wiring these 3 inside each of these 2 boxes. But with the assumption that in each of these pictures, what's going on in each of these respective boxes is kind of the same. But these pictures get a lot harder to draw than the nice ones over here. So one thing that we can do is sort of rotate our view sideways. And if we don't need to see as much about the wiring, we can treat this in sort of a dual manner like that. So when we do this, I'm going to write some terminology. We think of these little things, we've been calling them objects. We've been calling the outer ones subjects. And then one of these coalgebras we're calling projects. The terminology is changing, but the idea is that in a project, you can have some number of subjects of the project, which might be sort of like what someone on the outside might be seeing. Like, what is the subject of Topos? Talking about technology and ethics and ways we can use our math for those things. What are the objects of Topos? From that perspective, it's like us. But you can also look, inside one of the boxes, and inside the me box, I am the subject, and well, here I'm also an object, but so maybe there's not much going on in between there, but in the way I originally drew it, there were no objects in me. I am my own subject. I could go on. But I mention this because we use this in what is currently our main example. And just one last thing before I state that. One of the nice things about these pictures is it's easy to talk about stringing them together into some sort of hierarchy. And you often want to do some abstraction of saying, okay, well, we have some states of these guys, and we can forget about those, and they get absorbed into a state of this bigger organization. That was vague. Let me say something a little more specific. So this example is based on deep learning, in particular gradient descent. And so we have coalgebras SMN from T tensor M to T tensor N. Yes, I do. So T is going to be a polynomial where our contributions are real numbers, and our returns are tangent vectors at those real numbers. We could just write R there, it would be isomorphic, but this is a nicer way of thinking about it, which may become relevant in a minute. So that's what T is. Now what is this SMN? So SMN is a set of triples, M, F, and P, where M is a natural number, F is a function, a continuous function from R to the M times R to the little m to Rn, and P is in R to the M, big M. And you want to think of this as M is how many parameters do we have, P is what is our choice of those parameters, and F is what do we do with the parameters. So I'll make this more specific. So to specify this coalgebra, what we need is to go from SMN to a function from Rm to Rn. So I can tell you how to do that. Given M, F, and P, we get the function that sends X in Rm to F of P followed by X. And then we also need to know what to do on returns. So a return is going to be some y prime in T F of Px. So this is a tangent space in Rn. So that's going to be an n-dimensional vector. And so what this does, going back to, so we need to go from there back to something in Tx Rm. And what we do is we take so you can take the derivative of f, which gives you something like a matrix, take its transpose, which sends you backwards. That sends you to the tangent space of Rm plus m, little m, so we project onto the little m. And then we also need to get something in SMN based on this return. How do we update? And what we do there is same number of parameters, same way of treating the parameters, but then we change our parameters based on the return. So this is why we want to think of y prime as a tangent vector, because it's telling us how much and in which direction to change. And so we take our original parameters plus some epsilon, which we choose at the outset, times, so again, we apply the derivative of f, transpose to y prime, where over here it told us how much our x was changing. If we project onto the parameter space, that tells us how much our parameters should change in order to use the information given by this y prime, which we want to think of as telling us in which direction could we be improving. And so that's how we update. And something that we've checked is that this coalgebra structure satisfies the conditions of an adaptive, so, which are what I wrote over here. So I'll finish by saying that an adaptive is a structure like this, or the analog from M to N, which we have a nice formal definition of that I won't have time to write down, and that machine learning, or deep learning with gradient descent rather, gives us an example of that. And the way that I think of it in terms of these wiring diagrams, which is sort of what got me really excited about these things, is that we think of this function and the parameters involved as weights for how to combine the output of these different contributing pieces of information. And then the input comes in and kind of just affects the state. And so what I like about this picture is it looks very simple. And it makes me think that doing this in more generality and with more complicated wirings like what we have over there would actually give some kind of higher order thing that can learn. Also, I think this was inaccurate. The returns are actually distributed amongst the various contributors as well. But even so, this is a relatively simple picture, in my view, even if we have more things coming in. Whereas changing up the wiring and arrangement feels like a higher order kind of thing to learn, type of computer, perhaps. And so I'm really excited to see how we can interpret that compared to this. Thank you.
Cool, so anyone who wants to ask questions?
Yeah, so I guess this is a kind of to check understanding of what you just said. So there's a kind of, I don't want to say traditional, but you know, for a few years people have been drawing these pictures of deep learning with string diagrams. I think going back to Topos functor was probably the first one to do it, where you're kind of, like the string diagrams essentially depict the way the kind of training input is mapped to the training output, and also describes how the updates flow. That's the backprop part. But that's not the kind of picture you have here, right? Here, on the on the left-hand side, what's coming in is the parameter update that's being distributed to the various boxes, and what's coming out is not it's not the y, it's the function.
Well, it's still the y. So these two pictures are meant to be very different, as you pointed out. And the way that I think of it is that here what's really going on is like this is this whole box, and it sort of includes both the input and output, which we draw as kind of a single string here.
Right.
But here we say, okay, well, we've got the input coming in and the output. So this is like the result of applying the function to whatever we get from here. And then this is sort of the loss up what tells you, this is what tells you how to update your parameters.
Right.
And so you can do the same thing in here.
Okay, can I then ask, in the second picture, the lower picture, where's the, there's x and then there's like f of p comma x, which is y. So where's x here if it's not kind of?
Yeah, so you could say that like this box outputs some x1, x2,
oh, I see.
x3, and then here we decide to output, and so the state is p,
of course, I see.
and here we output f of p x, and then here,
right,
here we take in y prime, and then here this tells us how to distribute it back over to them and how to change p.
Right, okay, I see. The wiring diagram is what's being controlled by the parameter.
Yeah.
Right, okay.
P is the state of the system, sort of. You can think of moving these boxes back and forth.
Okay, that makes sense.
question of just names. What is the adaptive in the case? Is the new box or the...
So we think of the adaptive as the whole system. So an adaptive would be, so maybe I should have drawn adaptives over here because right now we're using that word to describe when we have some system of these for all m and n.
Deep learning is an adaptive.
Yeah, deep learning is an adaptive. And the sort of other simpler structures I described are examples of adaptives, but which are trivial in certain ways. Maybe they don't have an update, or maybe they don't have anything going on with like n not equal to 1. But this is an adaptive. This plus like a bunch of conditions on like algebraic structure on these SMNs that tell us how to combine them and show that and enforce that the update is compatible with that.
So you say a P tensor n to P tensor n coalgebra. So we're taking P to the tensor n as a functor, or kind of the functor is the. Sorry, I'm trying to understand to kind of decode what's the square, the bracket there. Is it functions from one to the other, or it's what is the?
So the technical version, so that polynomial, P tensor m to P tensor n bracket, is the same as this one, but with, I guess, that n replaced by an m, and this one given an n. And then you also have to, actually I think the rest of this definition would be the same. So,
Poly has an inner on.
Yeah.
And that's what that is.
Yeah, exactly.
It's a new polynomial.
If it was internal home from poly, because if I remember correctly, there are two, right?
Yeah, this is the one for
Mm-hmm.
tensors.
Yeah. Yeah, and so this coalgebra says, okay, we have all these different states of possible ways we can go from P to the m to P to the n, which I like to think of via these sort of portal-like interfaces, and it changes based on what state you were in before, what it's being applied to, and what the return ends up being. And all of that together gives you this new state.
Yeah, the thing that's kind of very interesting to me, at least, is this business that I gave this talk in the Finding the Right Abstractions, showing that exactly this picture of a manifold with a tangent bundle and stuff, kind of, where you need to think about the point where your tangent is touching.
Mm-hmm.
That corresponds to some sort of dialectical category for the traditional kind of dialectical category, and the point where the tangent is touching is exactly when, I mean, you don't remember because you weren't here when I was talking about dialectical categories over and over, but people who were here kind of might remember that on the first coordinate you have things that are like proofs, and these things are where your tangent touches the the tangent plane touches the manifold. So it's kind of, and it is exactly that same picture there, that the parameters kind of carry your tangent plane over the manifold. And I think it was very fun because it's the first time that I saw John by saying that he understood what I was talking about.
And that is on the YouTube channel.
Oh, great. I was going to say, I'd be interested in seeing that.
Yeah, no, it's just there. And, you can hear him saying that too, kind of saying, that's what you mean. So, it's just, I mean, it's not the same. It's a very similar picture. Where but it's different, right, David? Because it's on the level of the morphisms, not so much on the level of the objects. I know. I was just saying that it feels good.
Yeah, I'll have to look at that. That sounds really interesting.